Okay, on to question 3, which is on analog to digital conversion. So part A says, using a spectrum analyzer, you find that the maximum frequency f max in the signal above is 4 megahertz. What is the sampling frequency that must be exceeded in order to ensure accurate reconstruction of the signal at the receiver? So this is should lead you to the Nyquist rate equation, which is f of s, the sampling frequency, must be greater than 2 f max of the signal. All right, greater than or equal to 2 f max of the signal. So that is f max we're given here is 4 megahertz. So we need to be faster than 2 times 4 megahertz. And that gives us 8 megahertz is the sampling rate that we need to meet or exceed. So again, just this is if you see maximum frequency or the word that we're going to have in part B here, then you should think Nyquist rate and go from there. So part B is what negative effect occurs when it's less than the answer in part A, and that means we can have aliasing. And really that just means that if we're sampling too slowly that we don't see the sort of up and down of the sine wave, right? If we're not seeing both of those parts in some way, we're going too slow and we might be able to draw other waves that look like that one but aren't that wave within the frequency domain we're expecting to see. So part C, you decide to sample the signal at 10 megahertz, which is above our 8 megahertz rate. What is the sampling period at this frequency? So we're given frequency, we need to solve for period, which means that we need to solve for TS, which is equal to 1 over f of s, right? Usually our equation for period versus frequency is always t equals 1 over f or f equals 1 over t, right? They're inverse of each other. And so we have 1 over 10 megahertz using the units there. That should get us to our sampling frequency is 0.1 microseconds is our answer for part C. So then for D, draw the sample points on the figure above with your first sample point at time equals t0 microseconds. So we want to draw where we are sampling. So we start here. Again, we're just starting at 0.0. Then we go up by 1 microsecond and we sample at that point. We go up by another microsecond, we sample there. We go up by another microsecond and we sample there. We can pretty clearly see that like this wave is a little too fast for our sampling rate, right? Because it's going back over the x-axis multiple times in between our sample points. But regardless, we can see that we really just in this case, when we're told to sample at that rate, we find the sample point and we draw a circle there, right? We don't care about what else is happening with this wave in between. It can keep crossing the x-axis. We're just blindly sampling at the rate that we're told to sample at, right? So that's part D. Part E, assuming the maximum and minimum voltages that this analog to digital converter can support are 4 volts and negative 4 volts. What's the quantization resolution of this ADC? A reminder, the system uses a 3-bit quantizer, right? So these are the values we need for our equation. And we're going to use Q equals Vmax minus Vmin, which is just an equation you should have on your sheet, over 2 to the n, where n is the bits, is equal to 4 volts minus negative 4 volts over 2 to the 3, since it's a 3-bit quantizer. And that leads us 8 volts over 8 equals 1 volt. So we can tell when there is a change of 1 volt in this system, is what our resolution tells us. Part F, what are the first 6 bits of the binary output of the ADC based on the signal above? And so this is just making it a little easier for us. We have a 3-bit quantizer, so we need to go back to our graph here, and we're going to split up, we're going to divide the graph by half, and that gives us a 1-bit quantizer, right? We'd have either 0 here or 1 up here. Then we need to divide it again a second time. That gives us a 2-bit quantizer, which is like 0, 1, 2, 3 in binary. So we need to divide it up one more time. And then that means we have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, right? All of the values in 3 bits from 0 to 7. And that's our 3-bit quantizer, means like at each point we sample, we're going to give out, or we're going to output a value of 3 bits. So first 6 bits of binary output means we need to look at our first 2 sample points. So we're going to look here, and this sample point is in the 0, 1, 0 range, right? So we just find which set of values is this between, look over on the other side of the graph, and that gives us our value in binary. Our next sample point is here, so our value is going to be 0, 1, 1. I'll work through the rest of them, so 0, 1, 1 for the next one, 1, 0, 0 for this one, 1, 0, 1 for this one, and then 1, 0, 0 for the last point. So again, it's just find the point, find which quadrant it's in, and that's the value. So our answer for this would just be those first 2 points, which were 0, 1, 0, 0, 1, 1, since it just wants 6 bits. And then name one advantage of digital communications over analog communications. And this is usually the quick answer is going to be relative noise immunity, right? Because we're only sending 2 different values, it's easy to distinguish between there's relatively small number of values compared to the analog values that could exist. It's easy to sort of filter out the noise in digital communications. That's it for part 3.